This is section 1.3, part B. We're going to continue to look at the graphs of quadratic functions, or parabolas, but instead of looking at them in standard form, this time we're going to look at them when they're given in what we call vertex form, written this way. Okay. When we do this, we think of our parabolas as being transformations or changes or shifts to our basic graph, y equals x squared. We know y equals x squared is a parabola with its vertex at 0, 0, the origin. If I multiply that x squared by some number a, the graph either gets narrower, that's if a is bigger than 1, or wider, that's if a is a fraction between 0 and 1. If I multiply by x squared by a negative, that's going to reflect my parabola across the x-axis, or in other words, just turn it upside down. If I add or subtract a number inside the parentheses before I square, that's going to shift my parabola either left or right. Notice this is a little bit counterintuitive. The plus actually shifts left, and the minus actually shifts right. Finally, if I add or subtract a value outside of the parentheses, after the square, that either shifts my parabola up if it's added, or down if it's subtracted. We'll be using these same transformations with parabolas, but also with a lot of other graphs, other shapes throughout the semester. So it's a very good idea to get used to this now, because we'll use it a lot. When I graph parabolas this way, I normally find the vertex using these shifts, left, right, up, down, and then I calculate the zeros, like we did last time, by setting y equal to 0 and solving the equation. Equations in these forms are normally solved using the square root method. As we look at our first example, we're going to once again find the vertex, zeros, and y-intercepts in order to graph our parabola. I see that this particular function has a -4 inside the parentheses, which means it's been shifted to the right 4. And it's also got a -1 outside the parentheses, meaning that we've shifted our parabola down 1. If I think about going to the right 4 and down 1, that puts my vertex right here at the point 4, -1. All right, let's think about the zeros next. To get the zeros, or x-intercepts, we set y equal to 0. And we're going to solve this using the method of the square root method. I'll bring the 1 over to the other side of the equation, making it positive. And then I'll just take the square root on both sides. But keep in mind, when you introduce a square root, you have to be concerned with both the positive and the negative square root. On the left side, then, I'm either going to get plus or -1. And on the right-hand side, the square root and the square essentially cancel each other out. And so I just get x -4. This gives me two equations. X -4 equals +1, and x -4, x -4 equals -1, and x equals 5, and x equals 3 are my two zeros. To get the y-intercept, I'll put in x equals 0, so y would be 0 - 4 squared minus 1. Turns out to be 15, which is not particularly convenient to put in my graph, so I probably won't bother graphing it this time, although if I had a larger grid, I could do that. But let's go ahead and plot our zeros, 5 and 3. And I've got just a little tiny bottom of the parabola there, but at least it's enough for me to give some idea of what this thing looks like. Again, the vertex is the most important point. And so there's a rough sketch of my parabola. Just like before, we can identify an axis of symmetry through the vertex, vertical, would be at x equals 4. The domain of all real numbers. In the range, the smallest y value is -1, and then the y's go up to positive infinity. All right, we'll look at another graph. This one is f of x is -1/2 x squared plus 8. Starting by thinking about that -1/2, that actually does two things. The negative turns the graph upside down, reflects it across the x-axis. And the multiplier of 1/2 makes it a little bit wider than the standard parabola, y equals x squared. The plus 8 is going to shift us up 8. So the only real movement left, right, up, down is that up 8, putting our vertex up here on the y-axis at y equal to 8. So my vertex is actually 0, 8. To find the zeros of this particular parabola, we'll again set y equal to 0. I'm going to move the 1/2 x squared over to the left-hand side. So I would have 1/2 x squared equals 8. And then if I just multiply both sides by 2, cancels the 2 on this side, and I have x squared equals 16. Taking the square root and remembering the plus or minus, I would have plus or minus the square root of 16, or plus or minus 4 for my zeros. So I can plot those next. -4 and +4. The y-intercept I get by setting x equal to 0. So -1/2 times 0 squared plus 8 just gives me y equal to 8 as my y-intercept. And we actually already had that. It was also the vertex, so it doesn't give me any new points to plot. This is enough, though. I can visualize this upside-down parabola, and I can sketch it in. My axis of symmetry is going to be right on the y-axis this time, through x equal to 0, the usual domain of all real numbers. And this time I have a largest y value, so my range is going to start at -infinity and end when I get to y equal 8. In the next example, we once again have several transformations happening. We have a multiplier of -2, which is going to put us upside down again, or reflected across the x-axis. And also it's going to be a multiplier of 2, which is bigger than 1. It's going to be a little bit narrower than our y equals x squared graph. Next we have this -1 on the inside of the parentheses. That's going to shift us to the right 1. And then finally this +7 on the outside is going to move us up 7. So the vertex going right 1 and up 7 would be right here at the point 1, 7. To get the zeros, I set the y equal to 0. And let's move the first term over to the left, making it +2 times x plus 1 squared equals 7. If I divide by 2, I have x plus 1 squared equals 3.5. And taking the square root is going to give me x plus 1 equals plus or minus the square root of 3.5. I can move the 1 to the other side, making it a negative 1. Just got an extra set of minuses. There we go. X is negative 1 plus or minus the square root of 3.5. And I can just grab a calculator and come up with numbers. When I do negative 1 plus the square root of 3.5, I get about 2.87. And when I do negative 1 minus the square root of 3.5, about negative 0.87. Those are the zeros, or the x-intercepts. And finally, the y-intercepts, or y-intercept, I guess there's only ever one. We'll plug x equals 0. So y is negative 2 times 0 minus 1 squared plus 7. And let's see, that would be negative 2 times negative 1 squared is just 1 plus 7, which gives me y equals 5. All right, let's plot our zeros and our y-intercept. The y-intercept here at 5. And the x's, negative 0.87 is about there. Positive 2.87 around there. And I can sketch in my parabola. Like so. Axis of symmetry goes vertically through the vertex, mirror line for the parabola. And it looks like that would be at x equals 1 this time. My all real numbers for my domain. And again, there's a largest y value. So the y's start all the way down at negative infinity. And the biggest y value is 7. All right, one more example here. This time our function is x plus 5 squared plus 1. So our transformations would be left 5 and also up 1. So let's graph that. Left 5, up 1, about there. Puts us at the point negative 5, 1 for our vertex. The zeros. If I put y equal to 0 into my equation, and I bring the 1 over to the left and make it a negative 1, normally my next step is to take the square root of both sides, and I'll go ahead and write that out. Plus or minus the square root of negative 1 equals x plus 5. And I see that what I have on my left-hand side is an imaginary number. Can't take the square root of a negative, at least not in the real numbers. So I'm going to conclude that there are no real zeros, no real valued zeros. The y-intercept. If I put 0 in for x, oh gosh, 25 plus 1 gives me 26. It's certainly a valid y-intercept, but it's really, really large. Probably not something that's going to help me a lot, at least not with the size of grid I have available. So right now, the only point I actually have plotted on this is the vertex. I could give a very rough estimate because I know that this is not upside down, it's a right side up U. But I'd always like to get at least 2 more points to plot, 1 on each side of the vertex. So again, when I don't have enough information from the zeros, what I usually do is just make myself a quick little table of values. I like to put the vertex in the middle, negative 5, 1. And then I'm going to pick an x on either side, in fact the same distance on either side of the vertex, so that I can use symmetry to help me. If you don't move too far away from the vertex, the numbers won't get so large or so small that you can't manage them. So I'm going to stay somewhat close. Maybe I'll go to negative 3. If I were to plug negative 3 into my original function, negative 3 plus 5, try that again, negative 3 plus 5 squared plus 1. 2 squared would be 4. 4 plus 1 would give me 5 there. And again, use some symmetry. This was 2 away from the vertex. I actually added 2 to the negative 5. So if I subtract 2 from the negative 5 to get an x value of negative 7, symmetry tells me I should have the same y value. In fact, if you notice, if I change this negative 3 to a negative 7, I would now just have negative 2 squared, which would still give me 4. And I'll still end up with an answer of 5. So I often use that kind of symmetry to minimize the amount of calculating that I have to do. All right, we'll plot these. Negative 3, 5 is about here, and negative 7, 5 about there. And I can sketch in my parabola. All right, that vertical axis of symmetry, vertical line through the vertex, is at y equals negative 5. The domain, all real numbers. And the range, there is a smallest y value, namely positive 1, and the y values can get infinitely large from there. There's a bunch of practice problems next, so if you'd like to practice graphing some parabolas that are in vertex form, you can do that and can check your answers in the posted answers in my math lab.